very much. It's very nice to be here. So, like you've just said, my name is Mike Riley. I'm an architect technical director from BDP, and it's quite interesting actually. As Stuart was talking, I realised as he was doing New Bailey, I was just down the road doing the Ordsall Court. So we're actually working concurrently in Manchester at the same time. I think the critical thing from my experience is I tend to be working on these sort of large, complicated, and really quite difficult to deliver projects, and the University of Warwick sort of falls into that. And it, with BDP, we're a large international practice, and we sort of geared up to these sort of really difficult things, not only just in Manchester but across the whole of the world. So in terms of the project context, just to give you a bit of background before we start talking about the actual facade elements of the project, we've been working with Warwick for a long period of time. We've got our architects have been involved in developing the master plan for the campus. We've very much looked at how they use it, how people move across the site, where the sort of key areas of activity are going to be. It's a campus which has been in existence since the 50s and 60s, so a lot of their estate is actually reaching the end of its life, and therefore part of the project was about bringing their science department, their STEM department, actually into the 21st century. And it fits really nicely into their sort of their wider master plan. Critically, one of the things that they were trying to do is they were trying to create a really clear brief. They were talking about excellence in research. They were talking about sustainability. They're talking about actually trying to make interdisciplinary collaboration a lot easier for the department. And not only that, because it was such a central building on campus, it was all about the identity of what the faculty felt like. So there was a really strong drive from the client team to actually take all of these elements forwards. I think it's really important on these schemes to recognise that it's not just BDP that helps deliver these projects. We're working with some very clever people at Archetype and Arup, and some of their content's used today. In terms of what we're trying to deliver on that basis, there's sort of like 5 key concepts for the building. It's very important that it was a low carbon building. We're talking not just embodied carbon, but actually the operational energy that it uses as well. On that basis, how we decided to actually approach that was to actually go for a Passive House certifiable design, which is why Archetype were involved. I'm a Passive House certified designer as well. And we decided that actually to try and actually get that envelope incredibly efficient, effective, airtight, highly insulated, that fabric first approach is really important. And as with the previous presentation as well, examining quite hard things like the amount of solid to glass ratio in the buildings, how can we encourage a much more sort of dynamic facade, which actually builds on the solidity and the glazing in a very strong way. Because it's in the centre of campus, a key thing about that was actually business continuity. It was about not disrupting the student experience. Delivering quickly is very important to them. It's not disrupting the whole flow of what they do. So modern methods of construction are a very key part of this. It's bringing it in, it's making sure that off-site manufacture is maximised, and it's just-in-time deliveries, it's getting things in, it's getting them on the building, it's getting the building watertight and airtight. And then again, on part of that carbon conversation more than anything else, it was about flexibility. Some of the most flexible buildings are buildings that can be reused and adapted across their whole lifespan. The warehouses in Manchester are a good example of this. They're now houses, whereas before they were, factories and all sorts of other things. So that idea of actually making sure that the building was designed so that you can adapt it and adjust it, etc., is really important. So in terms of our approach, we've got the sort of standard way of you sort of looking at your embodied carbon. Your approach to net zero carbon. You've got your embodied, you've got your operational, and you offset to actually get to the principles of net zero. So this is a laboratory building that we're fundamentally doing. There was quite a lot of research at the start of the project to actually try and establish what is good in a laboratory context, because they are inherently very energy intensive structures. That's in terms of how they're built. So the floor to ceiling heights are different. They've got a lot of mechanical services and building services in the building. And therefore we actually looked at a whole range of different benchmarks to actually try to establish what would be an appropriate target. So we looked at things like the HOK Net Zero Labs Cup benchmark. We looked at different countries' net zero decarbonisation benchmarks, the LETI targets for commercial buildings. All of those things were taken in the round to actually go for a target for embodied carbon of about 650 kilograms per metre square, which is quite challenging in terms of a laboratory context. When you look at then the other projects that the university had actually done on their campus, they've taken quite a structured approach to their recent buildings. So they'd assessed their last 5 projects, IBRB, which was another science building, the Sports Hub, NAIG, which was a science building, and the business school and the Faculty of Arts. And as you can see from the sort of graph here, they had a widely variety in the results that they were getting. And when you look at that in the context of the project, you know, they were having simpler buildings with much higher carbon actually realised than we were actually going for. Part of our rationale then for actually saying, well, you know, this is obviously about performance gap. This is about something that is actually, you have a building that's designed to be low energy, because none of us designers want to design something that's inefficient or ineffective. So a lot of this is about the performance gap that's actually happening between the design stages and the construction stages of the project. So this is where the core principle of actually trying to get the Passive House certification came into the project. It's about actually trying to realise that highly engineered building and making sure that it's actually delivered to an appropriate standard. So when you look at the 2 targets on the screen, their latest benchmark for the Faculty of Arts building was broadly comparable to what we were aiming for a much higher energy-intensive building. So once we'd sort of done that, we'd done a bit of research, we'd taken a step back, we'd looked at what the industry was doing, where we were aiming towards, etc. We then challenged ourselves to actually start looking at how are we going to deliver to these stringent targets. And by analysing, you know, our experience and industry benchmarks, we basically looked at 4 categories of buildings, from refurbished offices through to general teaching, standard buildings, and then science buildings. And that's what the 4 different colours mean. And then when you go through it, you look at, you know, the FF&E, the finishes, the MEP systems, the facade, and the superstructure. And we identified very obviously early on in the project that, you know, by targeting the MEP systems, by targeting the facade and the superstructure, you can actually, that is your opportunity to make the biggest impact on your project. Because actually, if you save 10 or 20% in each one of those areas, you can effectively pay for actually getting the finishes and the furniture and the landscape without having to challenge it. So in that context then, we actually started to look very hard at actually how the building was planned out. I was talking about flexibility. Laboratories are actually designed as pretty much like offices on a very modularized grid. You have to have a certain distance between fume cupboards to lab benches, lab bench to lab bench. You know, it's a very rigorous setting out when you look at it. And if you actually can plan out the module of your building on a grid that suits science, then actually you can flip out the different users. So you could go for engineering, chemistry, you know, physics, whichever. Any of those could grow and flex naturally through the life of the building. So we looked at a matrix of, you know, grid sizes versus material sizes to really focus in on what the building should be made of. And we decided on where the function of the building was driven by human activities like collaboration, offices, etc. We could afford to go for a timber frame, a mass timber frame structure. Where we had more performance elements of the structure, we were going for something more like a precast concrete frame, because actually we needed it to be fairly stiff of a structure so that we could actually achieve the science that needed to be done. But we were assessing these all, every time we made a decision, every time we created this matrix, we're working it back to the benchmarks, we're working it back to our targets to see, in that framework, how we were getting on. The energy of the building in use was really important, and without looking at any of the detail, the buildings with a high energy usage are generally laboratory buildings. And then as they get to sort of more normal type of buildings, they're coming closer towards me. Our target was down there. So when you look at that as a sort of overall sort of ambition, it just demonstrates how committed the university are to actually trying to actually drive up their sustainability elements of it, because this brings students into the campus. The students are really interested in actually this type of discussion, because actually, you know, they care about it quite passionately. So in terms of trying to describe where it is, this is the campus of Warwick with our site right in the centre of it. It's surrounded by the library, the Oculus building, which is a general teaching building, and the arts centre. So it's right at the centre of the campus. And when we looked at all of their existing buildings in the context of our master plan, one of the things that this part of the campus was really looking out for was having a much more amenity and open space. A lot of it was taken up by service yards, etc. So we came up with this strategy where we took all the service yards, the back of house, the hard landscaping, we flipped it so we could create a university green and then wrap it with the science and engineering precinct. As a critical thing, because of the location on campus, was about actually then making sure that you were showcasing science, you were actually putting it in places where people could see into the building, and actually people movement through and those views into the scheme were really important. So actually creating heart spaces, homes, that's part of the identity for the campus, and it actually draws people into the core parts of the building. It's going to be delivered in roughly 3 phases. And one of the critical pieces is towards the top of the page, getting research and specialist teaching built as a brand new building enabled us to then unlock the rest of the site and deliver the rest of the project. These interdisciplinary sort of hearts and identity hubs then became the focus for people. This is where actually drawing people to. It's the natural entrances into the building, and it's where you can actually have all the joy. The science spaces have to be, they can be places that people enjoy being in, but they are very pragmatic in the sense that they have to operate. If you don't operate as a lab effectively, then it just sort of fundamentally fails. So in terms of the key elements of the brief then, that all came together with the MMC for the facade, precast concrete for the actual frame of the building. It enabled us to try and get the program benefits. The fabric first approach for actually making sure that we were being very effective, airtight, thermally efficient, using the natural ventilation, the solar gains, the shading, etc. on each of the facades was really important. And then actually getting in the sort of biodiversity and the low energy heating systems into the scheme. So onto the sort of, that sets the background of what it is and why it is. It gives you some sort of understanding as to how we approach the whole scheme, but then how do we actually apply it into the actual facade of the building itself. So when we start to look at the sort of phase 1 building, it's huge. It's 25,500 square meters worth of building, and it has to be that sort of scale to actually enable that decant to happen later. It has to bring a lot of the science into it, the specialist spaces, and it is generally like that. But there are some human-focused spaces, some general teaching, some cafes, etc. on the area that will actually bring people in. So we fundamentally looked at splitting our phase 1 building into these 3 core pieces. We've got the human-focused elements, which actually signpost the entrances. It's about bringing in sort of colour and texture so people really can interact with the building. You've then got a whole host of public spaces in the plinth where you've got lecture theatres, seminar rooms, some showcasing activity for the more exciting science. And then above, you've got this science wrap, which is an environmentally adaptive performance facade that wraps around the upper elements of the building. In terms of the human kit of parts, that first element of it, it was about making sure that we were creating shelter as you got up to the entrances. It was making sure the entrances were incredibly obvious and visible, so you knew where you were going and you understood how the building worked. And then when we've got people spaces like the Collaboration Hub, to create that identity, we were wrapping the facade of the Collaboration Hub in a similar sort of tone and material, again, to really give this sort of sense of where you are on the campus. We're very keen to actually sort of build upon the sort of traditions of the local area. Coventry and Warwickshire are very sandstone based, they're very solid buildings. And also that has translated into the Warwick campus. They're very proud, as you would expect, of the Fab building. It's shortlisted for the Sterling Prize. It's by another architect, but you can recognise the quality of the type of estate that they actually have on campus. So it's building upon those themes and those materialities in the human spaces, in those colonnades, is a really key part of the scheme. Then in terms of these public plinths, there's much more opportunity for this to be a bit more of a blank canvas. This is a bit more about where you can have your artwork, your showcasing. It can start to speak of science and engineering through the graphics, the iconography, etc., that you apply to the surfaces of the concrete. although I've talked about low carbon buildings, it's also very important from a university point of view that the buildings are maintainable and easy to sustain for a long period of time. So the natural thing that we explored very early in the process was, can we have timbers on the outside of the building? Can we have more sustainable materials? Can we have planting? And there was a strong reaction against that, because actually they want something which was much more classic, much more of a gateway into the scheme and part of the building. And then when you start to get up to the upper stories of the building, the science skin as a concept then has to react very strongly to the south faces facade and the north elements of the facade. The building is pretty much at a 45-degree angle, so it's pointing to the south, east and west. And we tried to organise the whole interior of the building, so it's all the spaces that you inhabit to do your write-up, your offices, and your sort of collaboration areas are all of them southerly facing facade with deep reveals that actually try to limit this sort of solar gain in summer, but actually allow it to actually lower the energy usage in winter by actually letting those free gains into the building. It's all mixed mode ventilation, so good analysis about prevailing winds, where are the pressures around the buildings. It's again going back to the idea of the science. There's a lot of noxious fumes that need to be exhausted from the building, so a bit of careful analysis about where do the fumes go, how do they disperse around the campus, how do we actually get to a point where it's safe for people to occupy was really key. And we used a lot of clever tools in this analysis to actually make sure that balance between the technology of the facade, what should the targets for the glazing be? How much energy should we let through the glass? How much light should we let through the glass is very key to this scheme, and it's been highly engineered down. And we made some unusual decisions at this point in the project. The usual thing, for example, would be to try and limit the amount of transmission of heat through the windows in the scheme. But in this instance, what we decided to do was to actually lower the performance in the glass, have a higher G value, so that actually it was getting at better energy balance in the sort of the spring and the autumn parts of the year. It gave us a much better energy efficient building. So when you start to talk about that adaptability and the environmental performance really sort of starting to drive the concept of the facade, this is where we started to think about how do we deliver the project, how do we actually clad this building and do it in a really efficient way that can enable us to become watertight and weathertight very quickly. So bringing in the sort of key briefing elements of MMC, the way we've approached this building is we've got a sort of backing panel that sits outside of the main structure of the building. And that backing panel actually very quickly is a unitized system that can be applied to the facade and the structure. And after you've done that, and after you've made the building sealed, you come along afterwards to actually add the fins and the concrete elements of the building. So everything can come to site in one big hit. As you can imagine, there's a lot of discussion about materiality for that backing panel. How do we actually make that an effective low-carbon piece of the structure? We looked at things like METSEC systems, stick systems, aluminium systems, concrete. In the end, what we've set as a standard, as a benchmark for the Stage 3 design, is this CLT lattice structure, which is a mixture of CLT timber slats, which are packed in the gaps with insulation. So they come as a structural system, but it's actually highly insulated in its own right. So rather than it being a solid timber panel, it's sort of like a mix, a little bit like a garden fence of solid and insulation. That then can actually fit it's all been analysed in the basis that we looked at how can we actually deliver this to site, how can we pick it up, do we need to span from floor to floor or column to column, and we've trying at this point of the project, because we're only at Stage 3, to actually make sure that we give the contractor teams that are going to follow us sufficient flexibility so that they can actually do the detailed design without fundamentally compromising the sorts of context of the building and the principles that we're trying to achieve. Because we have decided on a sort of really tight 7.2 metre grid as part of our layout and our module, it does mean that you can actually get huge strips of the actual facade to be delivered, and you transfer all the loads directly into the columns, which can lead to efficiencies in the superstructure. So we're starting to tie together the facade decisions we've made with the superstructure decisions we need to make. And I was talking about it earlier to say, we're targeting FF and MEP system structure and facades. They all start to interlink to each other in a very neat way. When we take that all in the round, we sort of set ourselves that sort of target originally of getting to about a figure of about 140 kilograms per square metre. We analysed each one of our material decisions against that target. So the two green graphs on the right are actually a concrete system, which is a bit more of a traditional, a bit more of a safe way of actually delivering this building. And then we actually analysed what are the advantages of going to this timber lattice work structure, this insulated CLT panel. And it showed that we can actually, effectively halve the impact of our structure into this project. As you can imagine, bringing timber into the external wall of the building actually meant that we had to have quite a lot of discussions with fire and insurance colleagues. They were very keen to make sure that actually if there were to be an incident in the building, you didn't end up having a huge amount of fuel that was on the outside of the building. And obviously that is a high consideration for them. So, as part of that, we came up with a whole managed solution where we used the Alliance of Sustainable Building Products guide to using mass timber frames, and we actually applied their methodology to not only the mass timber frame elements of our building, but also to the timber that we're using in the facades. So we took a risk-based approach to analyse how that would affect the operation building and also the life safety. By doing that in a very methodical way, it enables the insurance colleagues to actually get on board with the decisions. So in terms of materiality then, not what you would call classically low carbon materials. You've got concrete, you've got aluminium, and you've got timber-faced curtain walling systems, etc. I think the important thing that we're doing about this is that we are actually challenging ourselves to use the ultra-high performance concretes where possible. So it's actually thinning out the volume of material. It's about using cement replacement materials. It's about using aluminium that's sourced from hydro sources, so it's actually driving down the sort of energy use in production of the material and upping the recycled content as much as possible. But despite all that sort of science, fundamentally what we're trying to achieve here is quite a classic building. It's all about supporting the architecture and sort of good design for the structure. So this is a hot off the sort of press visual that we started to complete for our stage 3 work. It's the gateway into the campus now. It's a really classic structure which has got quite a lot of calmness to it. But then when you look at the university side, the university green side, where you've actually got the student focus, where the people are actually going to be dwelling the longest, it softens. We've brought in that red, we've brought in the materiality, the colour has changed, and it's actually made it much more welcoming as a building, from the sort of people-focused side of the structure. So that was a bit of a whirlwind tour of what we're doing and what we're up to, and I'm quite happy to take any questions if anybody's got any.
With the first instance, if that's okay. So one of the questions I wasn't asked is he was talking about, just like inherently labs on low carbon and a lot of emphasis with the mechanical ventilation. That sort of, how does that sort of work with getting that right in terms of how that utility sets with the facade?
Yeah. No, that's a really good question. We spent a long time thinking about those sort of things. I mean, fundamentally, there's a couple of things about that. One is because we're going for passive house certification. If you think about that in a classic sense, it's about houses, it's about taking out MEP systems, it's about really highly insulated facades. So there are parts of the building where you can say it's a classic approach to passive house and energy efficiency. So it's about making sure that the workplace and the seminar rooms, the lecture theatres all meet those performance standards. For the science spaces, what the certifier is looking for is they're looking for us to actually demonstrate that where there is a choice we've gone for a low energy version of it. So we've got, although it's one building, we've got 2 passive house models, energy models that are built. And there's literally a demarcation line that runs through the building that separates these 2 zones out. And what we have to say is we have to go to them and say, look, we've really minimized the distribution of hot water systems. So the losses in the distribution for air, vents, hot water, heating, etc. has been minimized. We've really got the air tightness, but then if you make the building airtight, the scientific equipment generates a lot of heat. So how do you get rid of that heat in an appropriate way? And how do you recycle it into the other parts of the building? How do you make sure it's captured and not wasted and just exhausted into the facade? And then you've also got this idea that you've got noxious chemicals in there. So some areas you've got process systems where they're sucking noxious fumes out, and that causes a pressure imbalance. So you've got to chuck a load of fresh air into the building just to counteract those process extract systems. So then it's all about controls. It's about, can they shut down? Can they turn down? Can you turn off air handling units in the plant room as you don't need them? You know, it's about making sure that things are only being used when they're needed, rather than being on 24/7 like they are in the existing estate. So yeah, it's a highly engineered, highly balanced, and quite intricate, really. And it will change, I think, as the building develops, because the science will change.
Yeah, I get that, Anton. Well, one maybe further to share any insight on the roofing side. So you've done all this work with facades. When there were any design how energy efficiency considerations in the roofing side were also some.
Yeah. So so what it's quite interesting, 'cause as a geek, I'm a bit of a technical geek. I've always classically sort of specified roofs to be sort of like an inverted system, because it's actually really robust. You protect the waterproofing layer. But what I've sort of learned by doing the passive house courses is that when they get wet, all the insulations, they start to dampen down, and they lose some of their performance efficiency. So on this building, we were very keen to actually track through the thermal line of the building and make sure that all of the insulation was kept dry and warm, and it was continuous around the whole part of the facade. There was then a whole load of discussion about, well, all right, if you've now got a waterproofing layer on show, is that going to be easily damaged? Because we're having solar panels on the roof, we've got other process extract systems that need to be maintained, there'll be people walking all over it. So then started to look at, well, you know, we've got biodiversity and other elements of sustainability, so can we put green roofs on there as well? And there was a whole bit of balance then between sort of, okay, so you've now got a potential fire source, which is the PV cells and the inverters that might break, etc. You've got green roofs, and you've got an exposed, potentially exposed waterproofing membrane. So there was a whole load of sorts of things that we had to look at from a technical point of view before finally settling on just effectively going for a warm roof system, because actually it gave us the best balance of everything that we could. And then it's about, which I think you'll appreciate, picking good quality products so that they're durable and they last a long time and they work really well.
I know that. She got curiosity, but man, and timber have said the science, with the woods, the foundation, and so on. What 5 reasons we have to achieve with that, and was it actually models and burns a system of the theoretical they should do so?
Yeah, no. Well, we could spend quite a lot of time on that one question, I think. I think it's quite important to recognise that there's nowhere in the UK that necessarily manufactures this type of product. In Europe, it's much more usual to use timber in the facade. So we've had to be very careful about what sort of certifications are available for these systems. We've also looked at American standards, some of the British standards, etc., to try and actually think about what is a good benchmark and balance of all the different systems that are available. To cut a long story short, what we've tried to do is we've picked products where there is a robust certification of full panel testing, mock-up testing, to sort of demonstrate how it works. And then you've got to take, in the next stage of work, when they do the detailed design, they'll have to take it to the next level, which is, how that one particular element performs in a fire situation, but then you're going to have to apply that principles to say, well, we've got insulation on the outside of it as well, we've got a window in it, we've got this, extra fins for the solar shading, etc. All of that sort of stuff has to be taken into account. So one of the things that the project and the university are considering at the moment is, do we need to actually fundamentally go for a full-scale mock-up? And there isn't necessarily, and this is a full-scale mock-up to test to destruction, to make sure that they fully understand, you know, the risks that they're sort of buying into. So on paper, it's been examined as, considering it's a stage 3, it's a developed design, it's a spatially coordinated design, but we've had to take it a bit further than we would normally do, just to try and reassure ourselves that we weren't actually fundamentally boxing the client into a, you know, an uninsurable building or a dangerous building. You know, these are the sort of things that BDP want to avoid from a reputational point of view. But, you know, Warwick also, you know, they can't have their flagship buildings burning down during construction. You know, it's just a really bad news story for them. So, you know, all of these things have to be seen in the round like that. And it does take a lot of effort early doors to actually make sure that we're covering the basis.
Brilliant.